Let us discuss higher order ordinary differential equations. So obviously we shall consider x as independent variable, y which is the function of x. So obviously y depends on the variable x. We consider the nth derivative of y as dny by dx n, and in short form we write y prefix n. The definition of differential equation of order n, which we already learned in our schooling level. The function which contains variable x, variable y, which is the dependent variable on x, and the derivative of y. The highest order derivative is called the order of the differential equation. Let us discuss the example. The first example, y double dash plus 3xy dash plus 5y equal to 0. If I ask you the question, what is the order of this differential equation, then what we do, we find the highest order derivative of y. In this equation, the highest order of the derivative is 2, so the order of this differential equation is 2. The second example is 5x raised to 4 y triple dash, that means the third derivative of y, 3xy y dash, the first derivative of y plus x square plus 1 into y equal to sin x. So again, to find the order, we find the highest order derivative term, which is third order. So order of this differential equation is 3. The next example is y raised to 4, right, in the bracket I written 4. So that means this is the fourth derivative of y, this is y into second derivative of y equal to xy. So obviously the order of this differential equation is 4. Now this equation, while this equation is called linear and non-linear, if the equation can be represented by this form, let us look at the form. The nth derivative of y plus pn minus 1x, that means some function of variable x into n minus 1th derivative of y. Similarly, some function of variable x into the n minus 2th derivative. We continue this sequence. Some function of variable x into the first derivative of y, some function of x into y equal to the right hand side, and right hand side contains only the function of variable x. If the differential equation can be represented by this form, then it is called linear, otherwise it is non-linear. We have the particular example here. Y double dash plus 3xy dash plus 5y equal to 0. Let us compare with equation 2. Is this equation in the form of equation 2 or not? So the coefficient of y double dash is 1. Highest order is 2 here. Then y dash. The coefficient of y dash is 3x, which contains only variable x. Y, which has the coefficient 5, which is a constant function, equal to 0. So this differential equation is in this form. So this is a linear form. This is known as linear differential equation of order 2. The second example, 5x raised to 4y triple dash plus this. This form, the highest order derivative term has coefficient 1. Here highest order derivative is 3, which must have coefficient 1. So we need to divide both sides by 5x raised to 4. So we have this form. After dividing by 5x raised to 4, y triple dash plus 3xy upon 5x raised to 4y dash plus x square plus 1 upon 5x raised to 4 into y equal to sin x upon 5x raised to 4. This is very simple mathematics. I just divided both sides by 5x raised to 4. Now let us compare the highest order derivative term, which has coefficient 1, y dash, which has coefficient 3xy upon 5x raised to 4. But this form says the coefficient of the derivative term y dash is this. The coefficient contains only variable x. It is the required thing. But here it contains x, x raised to 4, and variable y also. So this is not the function of x only, right? So that means this is not in this format. So this is non-linear differential equation of order 3. Let us discuss the next example. fourth derivative of y minus y into second derivative of y equal to xy. Consider the right hand side. The right hand side has variables x and y, but here we have given that right hand side must have variable x only, or the function of x only. So this is not the function of x only, therefore this differential equation is non-linear of order 4. The next example, x square y double dash minus 2xy dash plus 3y equal to 0. What do you say? You just think over this. This is linear or non-linear. This is the linear differential equation of order 2. Okay, now let us go for the next definition. Equation 2, which has the constant functions, right? So I mean, this is the equation 2. Equation 2 is what? The linear differential equation of order n, which contains the constant coefficients only, right? So I mean, the multiplier of the derivatives of y are constants only, then it is called linear differential equation with constant coefficients. The next definition is equation 2, which has 0 as the right hand side, then it is called homogeneous. So what is equation 2? Equation 2 is this linear differential equation of order n. If Rx equal to 0, this right hand side is 0, then it is called homogeneous, otherwise it is called non-homogeneous. We have the same example, x square y double dash minus 2xy dash plus 3y equal to 0. Let us identify the nature of this differential equation. We have already seen the order of this differential equation is 2. This differential equation is linear. That also we have seen. Now, what about the right hand side? The right hand side is 0. So when right hand side is 0, the equation is called homogeneous. Right. So this equation is called homogeneous. So what about this differential equation? This is homogeneous second order linear differential equation. The next example is third derivative of y minus 3 into y double dash plus 3y dash plus y equal to sine 2x. The highest order term is this. So order of this differential equation is 3. You can see that this is linear differential equation. What about the right hand side again? The right hand side is the function of x sine 2x, which is non-zero. So this is non-homogeneous function. Okay. So now if you have given any differential equation, we are able to identify its order, whether it is linear or not, or it is homogeneous or not. Now what is our goal for this unit? We are going to find the solution of the differential equation which are having this form, and we are familiar with this form. This is nth order linear differential equations. So two kind of linear differential equations we are going to discuss in this unit. Linear differential equation with constant coefficients. Constant coefficients means all these functions are having constant. The next is Euler-Cauchy equations. Today we shall not discuss the particular form of Euler-Cauchy equations. Today we shall discuss only the linear differential equations with constant coefficients. Okay, to find solution of linear differential equation with constant coefficients, we use two methods: undetermined coefficient method and method of variation of parameters. Before starting the solution, before starting these two methods, undetermined coefficient method and method of variation of parameters, let us discuss some symbolic mathematics. We define capital D as dy by dx. So what is the meaning of dy by dx? Dy by dx is capital D at point y. What is d? We know that d by dx derivative is an operator, right? So for operator we use, operator is the function. For function we use the symbol f, g, h. So here we are using the symbol d, right? So this is the function, the derivative function, which is evaluated at point y. Dy by dx equal to dy. d2y by dx square, right? So this is nothing but the derivative d by dx of dy by dx. d by dx is d, so this is d of dy. This is the composition function like f composite with f. So this is symbolically represented by d square y. If we continue this manner, then easily one can prove that d and y by dxn is nothing but d raised to n into y. Now let us look at this differential equation. What is this equation? The order of this differential equation is n. This is linear differential equation. Right hand side is non-zero. Then it is non-homogeneous. If it is zero, then it is homogeneous. These are the constants only. So this is nth order linear differential equation with constant coefficients. Now we are going to substitute d and y by dxn as this d and y plus n minus 1th derivative of y. So by this rule it is d raised to n minus 1 into y. Similarly this is plus n minus 2 into d raised to n minus 2y, and we continue the manner plus a1 d1y plus a0y is equal to rx. Now look at the left hand side, we take y common, so we have this form into y is equal to rx. Okay, now see, consider x in place of this d. So this is x raised to n plus n minus 1 x raised to n minus 1, same way like this. So this is the polynomial in terms of x. Here we have variable d, so this is the polynomial in terms of d. That is represented by capital F of d. So this equation is capital F of d into y equal to rx, where capital F of d is this polynomial of degree n. Right. Now let us go for the solution of the differential equations. So the nth order linear differential equation with constant coefficients is represented by this form, where f of d is this we know very well now. So we have given the same differential equation capital F of d into y equal to rx. Now to find the solution of this differential equation, first we consider the right hand side as 0, which is called complementary function f of d into y equal to 0. Then we have, this is like x into y equal to 0, then either x is 0 or y is 0, right? So when y is 0, then whatever f of d we have given, f of d into 0 is always equal to 0. So y equal to 0 has no physical meaning. We consider y is non-equal to 0, then we have f of d equal to 0. F of d equal to 0, which is known as an auxiliary equation, which gives us the solution which is known as the complementary solution. In the next lecture we are going to discuss how to find the complementary solution of the differential equation f of d into y equal to rx. The next part of the solution is known as particular solution. This is called actually particular integral. Y is equal to, we represent y as this 1 upon f of d into rx, then this is the solution of this is called particular integral, which is represented by ypx. Then the final solution is known as the general solution, which is the solution of this differential equation, is represented by the sum of the complementary solution and particular integral. So the general solution of this differential equation is y is equal to ycx plus ypx. In the next lecture, we shall discuss how do we find the complementary solution. So should we go for the exercise? We shall discuss the exercises in the next lecture to find the complementary solution of the differential equation.